My name is Jonathan Begum. This is going to be part 2 of the third project, solo assignment for EAS3810C. This part is going to be regarding the XFLR5 program. This video, I guess, actually I'm going to do another video following this regarding the bonus assignment, just to keep things a little bit more organized. So first and foremost, I'm going to open XFLR5. Just like this, wait till it loads up. I'm going to be showing a NACA 4410 airfoil. So in order to do that, we're just going to go down to direct foil design. Here we have a spline foil that's already here. It's symmetric, I believe. Yes, camber is 0. But we don't really need to worry about that too much. In order to get our NACA foils, we just go down here. We're going to type 4410, and we're going to change our panel nodes to about 220, just so have a little bit more for the computer to compute. As you can see here, we have 4% camber, and our thickness is going to be 10. So in order to actually analyze this airfoil, we're going to go to File. We're going to go to Direct Analysis. We're then going to go to Analysis up here, Define Analysis. And our Reynolds number is 375,000, just like that. We're going to leave everything else the same. Click OK. And we're going to go from -5 to 20 with you're going to want to do 1 degree increment, but because this has a little bit of convergence issues, I went and did 0.05. It's going to yield many more points, but it's also going to give you a more accurate curve. And if there's some uncertainty, you can find the local slope at or between the points that you need to find, and then kind of fill in the numbers that would correlate to that slope if there's any convergence issues. So I'm going to click Analyze. As you can see, we have a lot of convergence, and once in a while we'll come across an unconverged point. But we have so many additional points that we're accounting for that, again, we can use that slope of that lift curve slope to help find those uncertain, unconverged values. So we'll let that calculate really quickly. See, now it's starting to oh, there we go. It's converging and unconverging at the very last section over here. So this is where it's going to be helpful to kind of look at the data surrounding these points and then kind of make that, make a logical assumption that where that next point is going to come in. And you can also do an analysis specifically between, like, say 18 and 22 degrees with even smaller increments, and it might help with your convergence. So once this is complete, we can click exit out of this, and here are our graphs. So here we have our lift coefficient versus our alpha graph, and then we have our lift coefficient versus our drag coefficient. And then our other important graph is this lift coefficient over drag coefficient ratio to our angle of attack alpha. Now, all this data can be taken into an Excel file. In order to do that, you just want to right click on the current graph that you want, go to current graph, and then go to export graph. Just to give you an example, I'm going to just put it on my desktop really quick, click save. And you can do this with this graph and this graph as well as those two. So we're going to minimize that. We're going to look for our polar graph, just got written in. Let that open up. And as you can see, we have all of our data points all the way down to 19.25. But again, in order to get to this 20 degrees, if you're having issues converging, you can find the local slope between a couple of these points and then kind of just fill in what's necessary. And that will give you the general trend for what's going on with that airfoil. It reduces accuracy, but it also maintains continuity in your graphs. So again, this is the alpha, angle of attack, and the lift coefficient right here. And then you can just basically highlight and choose each of the numbers between increments of 1. So that's -5, that's -4, that's -3, and so on. You just bring that into a different Excel document. So I'm going to exit out of that. I'm going to exit out of this. Save. All right, beautiful. Let me delete this really quick. All right, so I'm pretty sure that's going to cover all in this video. In order to complete the other airfoil, the Eppler, all you're going to want to do is go to File, open your E385, and then you can go to File, Design, and you'll see that this the Eppler airfoil has been imported, and you just do the same exact thing as before. You change the Reynolds number and things like that and get your data and put it in Excel. And that is going to conclude this portion of the assignment. Make sure that when doing this assignment, you want to also do the Reynolds number of 1.25 or 1,250,000. But yes, that will conclude this assignment. And the next part of this bonus, or the next bonus or part of this assignment, excuse me, we're going to add some flaps at different angles or different degrees. But again, that'll be in the next video. So thank you for watching, and I'll see you in the next video.